lock on. There we go. All right. Okay. So today is more about those chords. So we're going to look at theorems about chords today. I told you guys this back in January when we were in the similarity and dilations unit, that anytime we have a theorem about something in geometry, once we learn about it, we get to use it as truth. So from here on out, everything you learn from this point forward, you get to start adding it to your toolbox of things that you get to use as techniques and strategies to solve these problems. So today, we are going to describe relationships among diameters and chords of a circle. We're going to prove and we're going to apply these theorems about chords of a circle. So today, it's all about the chord. All about the chord. So, the diameter of a circle and a chord have a very special type of relationship. In the circle below, we're going to draw a diameter. So let's all draw our diameter the same way. I didn't pass out rulers today, so just do your very best to draw a straight horizontal line through the center. That will be our diameter. Remember we talked about yesterday, a diameter is like a chord because it goes from edge to edge, but it has to go through the center of the circle. So there's our diameter. And then we're going to draw our chord. It says to draw a chord that is perpendicular to the diameter. Perpendicular, throughout the notes today, I'm going to be using this symbol. Excuse me. It's the upside down T. It means perpendicular. Okay. So perpendicular means that two things meet at what kind of an angle? 90 degrees. So it needs to be perpendicular to the diameter. So we got to draw it exactly vertical to make that happen. So just eyeball it as best you can. Okay. And then put the little box thingy to show that they are perpendicular. Okay. Now in part A, it says to use a ruler to take measurements. But here's the thing. I didn't use a ruler to draw straight lines. I hand drew it in, so those are not going to be perfect. I couldn't draw that, well I could. If I pulled out a ruler, I could have drawn these perfectly perpendicular. But I didn't. So we're going to make an assumption instead of measuring. So look at that picture. What does it look like the diameter is doing to the chord? What was that?
Making a right angle.
Well, we know that they're perpendicular. Cutting it in half, right? That's exactly it. It is cutting it in half. When something is cutting something else in half, we learned the word for this yesterday. It starts with a B. Bisects. A bisector, right? The diameter is the bisector of the chord. So that's what we notice. We're going to write that down. The diameter bisects the chord. If you don't remember what the word bisect means, you got to get used to it. It means cuts in half. Okay. All right. Then it says to compare your answer with your neighbors. We didn't do that because we're doing everything together. Okay. So it says, what conjecture can you make based on your investigations of a diameter perpendicular to a chord? So basically, they're asking, whenever we have a diameter perpendicular to a chord, will it always bisect the chord in half? What do you think? Yeah, that's why we're pointing it out. So we could use this as truth. In fact, number 10 from the homework would have been a lot easier if we knew this yesterday. But that's how it's going to be. We're going to be learning new things to add to our tool belt each day as we go. So here's what I want you guys to put. When a diameter is perpendicular, put the upside down T for perpendicular to a chord, comma, the diameter bisects that chord. So that means that this will always happen. So we get to use this as another tool in our toolbox. We'll put little stars next to it. So anytime you see a diameter or a radius, because a radius is half a diameter, hitting a chord, and you know that it's perpendicular, then you can assume that it's cut in half. Or if you see a diameter radius hitting a chord and you know that it's hitting the halfway mark of the chord, then you can assume that the angle that it hits it at is a 90-degree angle. Okay. So there are some assumptions that you do get to make, but it's never about the picture. It's always about the information. Okay. Turn the page. So on this next page, we've got a proof here, and it says, for the theorem below, the statements for the proof have been scrambled. Rearrange them in logical order. So we are going to look at this proof, but we're not going to prove it. We're going to pretend that we do. We're not going to go through the whole thing. It's really long. Okay. There is going to be another proof that we will go through in this lesson, but not this one. Okay. But we do need to look at the theorem because it's important. So we've got this picture, and it says theorem. In a circle, two congruent chords are equidistant from the center of the circle. If you guys have a highlighter, I do want you to highlight this theorem because it is another tool that we can add to our toolbox. Something that we can use, more information, okay? So, and I also want you guys to circle the word equidistant. Over on the left, it talks about equidistant. If two segments are the same distance from a point, they are equidistant from it. Equidistant is like saying equal distance, right? It's the same thing. All right, so we are given chord AB is congruent to chord CD. So I'm just gonna trace them with my highlighter. Chord AB and chord CD. They're congruent, that's what it says, it's given information. We're also given that RX is perpendicular to CD. So RX is this segment, and it already shows the little box thingy to show that it is perpendicular to chord CD. And then RY is also perpendicular, but to chord AB. They want us to prove that RX and RY are congruent, that these chords are equidistant from the center of the circle. What ends up happening, of course, is it gets proven to be true. So we get to use this as common knowledge. So this is going to be a proof that you're going to be using a lot. So as long as you have two chords that are congruent, as long as you know that they're congruent and they're in the same circle, you can assume that they're going to be equidistant from the center because of this theorem. So now you get to add that to your toolbox, okay? All right, go ahead and turn the page twice because the next page is also the same proof. We're on page 448 now where it says number 4 right at the top, okay? So it says, given EF is congruent to AB, and what they're referring to is this picture right here on the left. You got a circle and a circle. Those are called concentric circles. Whenever you have a circle and a circle, it's concentric. And it says explain how you know that EF and AB are not equidistant. We know that they're not equidistant from the center R. So let's investigate. Why are they not equidistant from the center? Well, we technically have two circles here. And EF is this chord. And it's congruent to AB, but AB is over here. Why wouldn't those two equal chords be equidistant? What makes them not equidistant? What do you think? I got your point, I got you, yes. So what she was saying is that EF is a chord on the smaller circle. AB is a chord on the bigger circle. Yeah, they are sharing center R. They're concentric, but they're not on the same outer ring. They're not on the same ring. So even though they are congruent, that's why they're not equidistant. They're not on the same circle. That's why. So we can say EF is congruent to AB. Notice I'm using the congruent symbol, not the word. If you want to write it out, that's up to you. But EF is a chord the outer circle. Therefore, they aren't equidistant. Yeah, as you guys remember from January, there was a lot of writing in geometry because there's a lot of definitions and theorems that we have to establish. And that's why I use my abbreviations, my symbols. Okay, we're gonna use a lot of that. All right. We're gonna critique Michael over here. Michael draws two congruent circles. So we know that they are congruent, and there's two of them, but they are not concentric. So they're not like the picture up here. They're not concentric, but they are two congruent circles. So that means that we have two equal circles, but they are separate from each other. So pretend that you have two exactly equal circles. Obviously we're drawing them by hand, so they're not going to be exact. And make sure you put a center in your circle. They look like beady little eyes. Okay, now let's continue reading. He then draws two chords, one in each circle that are the same length. So two chords, one in each circle, they're the same size. So I'm going to draw one kind of angled. And let's pretend that the other one I draw is the same size, but I'm going to draw it at a different angle in the other circle. But they're the same size. It almost looks like an eyelid now. And because these are the same size, we need to put the little tick mark that shows they are congruent. Now it looks like a Frankenstein eye. He claims it is possible that the two chords are different distances from the centers of their respective circles. Is he correct? We learned on the last page that when we have two congruent circles, or not two congruent circles, two congruent chords of the same circle, that they're equidistant. Now these circles are not the same, but what do we know about them? They're the same size, they're equal, they're congruent. So isn't that technically the same thing? So shouldn't these chords be equidistant then? Yeah, they are. So is he right then? No, they're not different distances. So nope, Matthew's wrong, or not Matthew, Michael's wrong. Congruent circles have congruent radii. Remember that's plural for radius, comma. So the two congruent chords will be the same distance from the centers. Centers, not center, because they're two separate circles, but they are equal in size. Okay. So this extends our theorem now. It doesn't necessarily have to be in the same circle. If we have two circles that are congruent, then we can treat them like they are the same exact circle, because technically they are. They've got the same properties. All right, let's try number 6. Check your understanding. So it says, a chord of a circular clock is 12 inches long. I'm going to stop because I don't have a picture of this clock. We're going to need to draw it. So draw a circle. Don't make it too small because you need room to add stuff to it. Put a center on your circle. And it says we have a chord. A chord of a circular clock is 12 inches long. Don't overthink drawing this in. You could draw your chord anywhere in the circle that you want. In my opinion, it's the easiest just to draw it horizontally at the top, okay? It says it's 12 inches long, so let's put 12 on that. Then it says, and its midpoint is 8 inches from the center of the circle. So the midpoint is the middle of the chord. That's the the middle of the chord, and it says 8 inches from the center. Now, here's something that we just learned. Well, at the very beginning of the lesson. When we have a diameter that hits a chord, and since this is at the midpoint, doesn't that mean that each of these sides is 6? Because that's the middle of the chord. So this side is 6 and this side is 6. Well, now this is not a diameter, this little 8-inch section here, but isn't it part of a diameter? Right. So that means it's hitting that chord at what kind of an angle? 90, right? Okay. So what theorems can we use to determine the length of the radius? We do not have a radius drawn on our picture. So let's add one. Let's add a radius in there. So I'm going to add one right here. Why do you think I added it right there? To make a right triangle, right? Because what do you think I'm going to use now? The Pythagorean theorem. Exactly. Just like yesterday, you're going to be using right triangles and Pythagorean theorem a lot. So it says what theorems can you use? We're going to be using the Pythagorean theorem, obviously. And we labeled some things on our diagram, like the 6s and that right angle, because a diameter bisects a chord. That was one of the first things we learned in today's lesson. So those are 2 theorems or definitions that we are using to answer this. So we're going to find the radius. So I'm going to label this radius as R. But what side of the right triangle is R? The hypotenuse. So that's our C technically, but we're using R instead. So for part B, let's actually find the radius. And how would I set up the Pythagorean theorem? Got it. Okay. You guys have gotten so good at Pythagorean theorem. We used it a lot. You guys did well on that unit test. What is 6 squared? What's 8 squared? Anyone know 36 plus 64? 100. Ooh. Now what? Square root it. You guys can do these in your sleep. What's the square root of 100? 10. So the radius is 10 inches. It gave us units, so we have to make sure to give it back in the answer. Okay. So that was number 6. Let's also do number 7. Number 7 says a chord of a circle is 15 inches long. And then stop. What do you think I'm going to make you do now? Draw a circle, right? We got to draw a picture. Guys, the first several problems on your homework, you're going to need to be drawing circles. You're going to be drawing a lot of circles tonight. So we need a circle. Okay. Mark a center of your circle. And we need to draw a chord. I'm going to draw it the same exact way I drew it in number 6, because it doesn't tell me how to draw it. As long as it's a chord, it's fine. Okay? If you wanted to draw it at an angle like we did over here, this little eyeball, you can do that if you want. Okay? I think it's easier if we just keep it simple, keep it basic. All right, it's 15 inches long, so label it 15, and let's continue reading. It says, and its midpoint is 9 inches from the center of the circle. So the midpoint, the middle of the chord, hits the center, and it's 9 inches away from the center. All right, we're hitting the midpoint of the chord. So that means we can cut that chord in half. What's half of 15? 7.5. So this is 7.5, and this is 7.5, which means that this little segment from the center hits the chord at what kind of an angle? A 90, right? Okay. Then it says to calculate the length of the diameter. Well, we need a diameter, but I'm not going to draw a diameter. What kind of a length am I going to draw in here? What do I need to make? A right triangle. So I can make a right triangle with what I have there. But what kind of a length do I have to draw in that circle? A radius, right? So let's do the other side this time. It don't matter. This is the radius though. So remember, it wants the diameter. A diameter is how many radii? It's 2. So if I find 1, all I have to do is double it, and then I've got the diameter. That's it, okay? So what theorem are we using? Pythagorean theorem. How would I set it up? You got it. And then we just got to do the math. So 7.5 squared, I'll give it to you, because my calculator's way over there, is 56.25. What's 9 squared? 81. And then what do we have to do with these numbers? Add them. When we add them, we get 137.25 equals r squared. And what's the next step? Square root it, right. Now, when we square root this number, is it going to be a whole number or a decimal? It's going to be a decimal. It's not a perfect square, so it's not going to be a whole number. So we're going to have to round it, and it's going to end up rounding to 11.7. But this is just the radius. What do I need to add to this to find the diameter? Another 11.7. What's 7 plus 7? 14, carry the 1. 1, 1, 1 adds up to 3. That 1, 1 adds up to 2. So it's 23.4. So D, the diameter, is 23.4, and the units were inches. Like I said earlier, most of the time, you're going to be trying to make a right triangle using Pythagorean theorem. Okay? We're not doing number 8, so we're skipping that part. Go ahead and turn the page over. Number 9. This proof we are going to complete. And that's because it's short, sweet, and to the point, and it's extremely important, and it's fill in the blank, so it's not going to be bad. Okay? So, we're going to complete the statements for the following proof. We are given chords A, B, and C, D. So we've got chord A, B is this chord. We've got chord C, D is the other chord, and they are intersecting inside of a circle. And it says to prove that AX times XB equals CX times XD. So what's going to happen is we are going to prove this to be true. And then we'll be able to use that to solve problems when we see situations like this in a circle. So we're going to start with the statement and reason. Notice both of those are blank. That's because they expect you to know this about a geometric proof. You always start it with what's given. So the reason is going to be given. And we got to look at what was given. Chords A, B, and C, D. So this is exactly what we have to write for statement 1. Chords A, B, and C, D. Remember I told you in January that you won't be required to complete a proof on your own. You do need to understand how to read a proof, how to follow a proof, and understand what it means, what it represents. Now, in number 2, statement 2, it says draw AD and CB. And that's because we can draw a line through any 2 points. Okay, that's just the definition of a line. So we're going to connect A and D together, like so. And we're going to connect C and B together. And it makes that little twist tie situation. Okay, you've seen this before. Remember similar triangles, side angle side, the vertical angles, angle similarity, those types of things. They're coming up again because this is geometry. Number 3, because of this twist tie situation, we can say angle XAD is congruent to angle XCB. So XAD, X to A to D, the middle letter always tells you where the angle is. So it's angle A, okay? I'm putting a little line there because it's congruent to another angle. The other angle it's congruent to is XCB. X to C to B. So remember, the middle letter is where the angle is. So these 2 angles are equal. They're congruent. It also says XDA is congruent to XBC. XDA, I'm going to mark that with 2 lines. And it's congruent to XBC. So this one down here. The reason why we know that those angles are congruent is because of this reason right here, and I want you to get your highlighters out. I want you to highlight this statement on number 3, or the reason on number 3. Two inscribed angles intersecting the same arc are congruent. Okay? I'm going to show you what they mean by that. So first of all, let's look at the two angles that are congruent. Let's look at angle A and angle C. Look at the arm of angle A, its arms. The first arm ends at D. The second arm ends at B. So this is the arc that it is intercepting. This angle intercepts arc DB. The other angle that it's congruent to, this angle C right here, it has an arm at D and the other arm at B. Also, it intercepts the same arc. So anytime you see a circle and you have angles inside the circle, they're inscribed. If they meet up at the same arc, then you can assume that those two angles are congruent. The same thing happens with these two angles. If you look at angle D, it has arm that leads up to A, its other arm leads up to C. So it intercepts arc AC, but so does this angle. It has an arm that leads to A and an arm that leads to C. So it intercepts the same arc. So then those inscribed angles must be congruent. But an inscribed angle has to look like this. It has to be inside the circle. The end points of the angle are on the arc, and the inner coordinate of the angle has to be on an edge of the circle. Okay. So that's what it's going to look like. All right. So you can use that from here on out. Another tool to add to your toolbox. Number 4. Now we have triangles. Triangle AXD and XCB. We've got two triangles here. And last January this year, we learned how to show that those are similar. We don't have any numbers, but we know something about two pairs of angles. So how are those two triangles similar? Angle, angle. Right? We got two pairs of congruent angles. So angle, angle. Because they are similar, that means they are proportional. Similar triangles are proportional. The reason why I'm writing this for the reason on number 5 is because in the statement of number 5, we've got a proportion. They took pieces of the sides of the triangles and they set them up as they're similar because they're similar triangles. When we solve a proportion, a fraction equal to a fraction, what did we do? We talked about it yesterday. If I were trying to find a variable here, how would I handle this problem? Cross multiply is right. Jackson got it. Right. So that means we would have AX times XB equals CX times XD. And guess what? That's what we were trying to prove. So now that we've proved that, now let me show you how to use it. So basically, what this means is this will always be true. Whenever we have two chords that cross inside of a circle, that means I could take the pieces of one chord, multiply them together, set it equal to the multiplication of the two pieces of the other chord. So let's look at number 10. This is going to wrap it up for us. In the circle shown, what is the measure of x? We just learned how to handle this. We've got two chords here intersecting, making 4 pieces. I could take the 2 pieces of one, multiply them together, set it equal to the other 2 pieces multiplied together. So I can have x times x equals 49 times 4. What is x times x? X squared. Anyone know 49 times 4? Oh, 196, thank you. That's a special number. What's the next step? Square root it. What does x equal? It is a perfect square. Anyone know it? No? Can you make me grab my calculator?
Is it 4?
No. What's 4 times 4? 16. So it's definitely not 4. It's 14. So x equals 14. And that's how you're going to do some of the problems on your homework as well. Okay? So your homework is the PDF on Google Classroom, numbers 11 through 20. I should see lots of drawings of circles when I check your homework tomorrow.